All right, hello everybody. So this video is just kind of like an intro to the content of Module 5 here. So we're sort of transitioning from the stuff that we talked about in binary search trees into the new stuff that we're going to talk about. So if we look at our sort of binary search trees here and sort of like take a zoomed out view of them, they behave kind of like sets, like in the sort of mathematical sense. Don't know why I'm using blue, I usually use green, don't I, right? So like a mathematical set only supports operations for checking to see whether or not a value is in the set or not here. Now, because we're trying to treat these as data structures, right, we also have operations for adding and removing values. But the main thing you can do is you can sort of ask, hey, is this value in the tree or not, right? If we do a find and it returns a non-null pointer value, that means the answer is yes, this key is in the tree. And if it returns null pointer, that means no, this value is not in the key here. So that kind of matches the sort of mathematical definition of a set. It's a thing that holds some values. There's no duplicates, just like our binary search trees, right? And the most important operation is sort of drawn like this in math, and it's the is this element a member of this set sort of thing there. It's a true-false kind of thing here. You can ignore this part here. That's for math nerds. Put it another way is, like, if you have a binary search tree and a key, not a value, a key, we're going to use the word value for something different. The only sort of information we get is true false, right? So true is yes, this key is in the tree, and then false, no, this key is not in the tree. That's all sort of all we kind of get out of it there. Now, obviously, a binary search tree is not the only sort of thing that you could build that would kind of fulfill these like sort of requirements here. So you could take your ordered array class from assignment 1, and you could use it as this kind of thing here. Just modify it to forbid duplicate values, and then the exists function, right, tells you whether or not a value in it exists. And you could use like a binary search or something to speed that up there. You could consider just a plain old array or vector of bools to be a set here like that. So if I have an array whose values are like trues and falses here, then each index between 0 up to the array size -1, you can think of that as like, okay, you can ask, is 0 in the set? And if the value is true, that means yes. If the value is false, that means no. So it's like a set that sort of potentially contains all these sort of different items here like that. There's a ton of other ways you could sort of structure this, right? And they'd have different like, big O runtimes and stuff there like that. Now, a lot of times, instead of just wanting this sort of true-false thing of like, is the key there or not, right? Is it there or not? We want some additional information. So, for example, I might have like a list of student names, and I want for each student their GPA. So for a given name, I don't just want to know, hey, do I have information about this student or not? I want to know what is their GPA. So it looks something like this, like a table, right? So we have each name, and each name is sort of associated with a floating point value, right, which is that person's sort of GPA. So if you have something like this, this is called a map here. It's kind of like a generalized array, right? It's an array where you can think of these things here in the first column. Those are like our indexes, but they're not like numbers, right? They're strings, right? So you can look up an index, and then you get the value in the sort of right-hand column there. So we want to build something that works like this here, where it's like, okay, I can look up a name and I get that person's GPA, or I can look up a name and I can update their GPA or something like that. So you can represent this as a binary search tree where we store the GPA as a float inside of the node structure, but we don't use it to like organize the tree. It's just kind of like along for the ride here. So the tree is organized around the keys, around the string part of it's there, which represents the person's name. And then the float, the GPA, just kind of like hangs out there. They don't affect the tree structure at all here. So when we do like our left is less than, we're doing that on the names. When we do right is greater than, we're doing that on the names here. So like here's an example of this, right? So I took this table here, right, the same one from the previous slide there like that, and I built a tree out of it here. So my tree is organized around the names here, sort of like using alphabetical comparisons. So Bob, alphabetically, is less than Jane, right? Because B comes before J. So therefore, Bob is to the left of Jane there. Likewise, Al is less than Bob. Rachel is greater than Jane, etc., like that. Note that that's not true for the values, right? The GPAs are shown underneath at the sort of bottom half there like that. And there's no left-right organization about those here. The left-right organization is purely about the names here. So given this sort of structure, like what can we do with it here? So when we insert things into it here, we have to supply both the name and the GPA. Sure, you can't just sort of like insert a person. You have to say like what their GPA is. And then when we insert them, there's a new possibility. What if the person, the key, already exists here, but the GPA is different? So in that case, our insert does something different. We update the value. So this is like, there's sort of two versions of insert. One is if you insert something that we've never seen before, we create a new node. But the other is if you insert a key that we've already seen, like that node already exists. Just like other BSTs, we don't create a duplicate, but now we have a new value. So we just update the node that we already have with the sort of new value here. So we sort of treat these as the same like function, right? Insert does both. If K does not exist, it sort of adds it. Otherwise, it just updates the existing value there. We can still find a key here, but when we find a key, we don't just get like, hey, is it there or not? We get its value inside of it there. Assuming our tree is balanced, right, this takes log of n time to find a key. If you want to find a value, you have to search the entire tree, right? The tree doesn't have anything that sort of makes finding values faster. It just has things that makes finding keys faster. And likewise, duplicate values are allowed, unlike keys, right? There's only one person in our tree named Jane, but there can be multiple people with a 4.0 GPA. And of course, you can remove a key from the tree, which also removes its value because the value is stored in the node with the key there. So like I was saying earlier, you can use this as kind of like a generalized array here. So a standard array, right, has the keys are integers from 0 to some k minus 1. Those are our keys, right? And then the values are just like whatever stuff are you storing in the array. So if you have an array of floats, right, the values are floats there like that. The values that you store in the array, those can be anything, but we don't have a choice for the index. The index is always going to be an int 0 to the array size minus 1 there. So a map sort of removes this restriction here. A map can have any type as its index there. So like our indexes are sort of type string. The code that we would use to sort of like, update Bob's GPA to 3.8, like we would literally write this, assuming we have a map object there like that. But you can kind of imagine this having the syntax to make it look like an array, right? Like that. And in C++, you can actually do this. You can overload the square brackets operator, and in fact, the built-in map header sort of does this here. So you can kind of imagine that like what we're building is sort of like a weird array where the indexes are strings rather than just sort of normal integer values there. So we can sort of compare the maps that we have with sort of standard arrays if we do this here, right? So maps, our indexes can be anything, whereas for arrays, they can only be non-negative integers, right? There's no array that has like, negative indexes or anything like that, right? Our values can be anything. That's the same for arrays here. Lookups, if we're using a binary search tree, are going to take log of n time, whereas an array offers constant time lookups. So arrays are sort of win there. And then memory usage for a map, again, assuming that we're building it on a binary search tree, is O of n, where n is the number of key value pairs that we're actually storing. So it's the number of people that we're storing information about here. For arrays, the memory usage is O of k, where k is the largest allowed key here. So with an array, even if you're not actually using all the array entries, they all exist. They all take up memory. If you're like, oh, I need to be able to use any index between 1 and 1,000,000, all of those million array indexes exist, not just the ones that you're using. With a binary search tree, right, only the nodes that we've actually added take up space there. There's a word for this here. We say that binary search trees are sparse in their memory usage because they only store what you actually put in them, whereas arrays are dense in their memory usage. They store all possible things, not just the things that you've actually put into them there. Oh, hey, here we go. Right. Arrays are dense. Yeah, they store all possible keys, Whereas maps, if we do them as binary search trees, are sparse. They're only storing the keys that we sort of actually use there. And that's kind of like a requirement, right? Because like if we're using strings, we can't sort of say, well, I'm going to pre-allocate all possible strings. I just need to store the ones that you've actually sort of given me there. So sparse memory usage is sort of like we're gonna have to do that for what we want to build here. If we build this on top of a binary search tree, then all of our operations will run in log of n time, assuming that we're using a balanced binary search tree. Sometimes that's a little bit too slow. We want something closer to the actual constant time performance of a true array, but we still want to get the freedom of a map, of having arbitrary sort of index types here. So that brings us to our next things, which is hash tables. So hash table is another way of building a map, right? It's another way of sort of building the map abstract data type that gives us constant time lookups. But the trade-off is memory. While the memory usage is like still technically sparse, it's actually like really big here. So it's going to be something like 100 times that of what we're sort of actually using or something like that. So the next video, we'll look at the implementations of hash functions, and then we'll sort of see how they can be used to implement hash tables next week. But after hash functions, I'll sort of give you a video about the assignment 5, which is the assignment for this module. But that's sort of like your intro to what we're going to talk about this week here. Thanks a lot for your time, everybody.